What I'm going to focus on today is our project with Blue Waters using the Community Earth System model, one of the top climate models in the world, to examine, basically to do much more detailed analyses and as well as uncertainty analyses than have been done previously. We think that the results we'll be getting out of this, and we don't have them yet, as I'll explain, are really going to be quite important within the atmospheric sciences community. First of all, climate change is one of the most important issues facing humanity. The changes we're seeing in the Earth's climate system are very real. They're based on observations, but models are extremely important to us as well as the tools we use then to project future changes occurring in the Earth's climate system. We could talk all day about the effects of climate on humanity and ecosystems and why this is so important to us. Last week we released the National Climate Assessment, which is a special report that is required by Congress. And I suggest that if you want to learn more about climate change, and I hope you all do because I think it's important to us all as well as to our children and our grandchildren, that you go to NCA 2014, so NCA 2014.globalchange.gov, and you can learn a lot more about that assessment and what it says about what is happening to our climate system and what's likely to happen over this century. The projections for climate change, the pathway we're currently going, which is through in the heavily burning of fossil fuels, suggests that we will have as much as an 8-degree Fahrenheit increase in temperature by the end of the century. But that's not what all climate change is about. It isn't all about global warming as implied and sometimes in the press. It's really about the changes in severe weather, changes in sea level, and many other aspects that are likely to have a huge impact on humanity. But even at the 8 degrees is quite large if we were to achieve that high, and hopefully there's many other pathways we can follow by choosing to move away from the use of fossil fuels or from reducing the emissions into the atmosphere, at least from fossil fuels. That could take us down a lesser pathway. But 8 degrees is quite large. You know, if you look at an ice age, the last ice age was about 15, 17, 18 degrees cooler than now. And so when you talk about an 8 degrees warming, that's an appreciable warming on the Earth compared to the past. Well, the focus here is on CESM. This shows the original grid in the model when we were starting the project, which is the finite volume version. This model tries to account for all the basic physics in the atmosphere, including parameterizations of the kind of clouds that were just being discussed. We don't try to look at those clouds in the kind of detail as was being discussed earlier, but we do try to account for all the effects they have on the atmosphere. But we also try to account for what's going on in the oceans, on land. We need to account for chemistry in all of those places as well as biology. So it's a very complex model that trying to represent all these different processes. The newest version, which was used in this project, I'll be discussing in a minute, uses a new spectral element approach for what's called the dynamical core, for the way we can represent the atmosphere and the oceans. That allows us to much better take into account the high resolutions we want to be able to run at and to be able to run on a machine like Blue Waters. Well, one of the reasons we want to go to extremely high resolution with such a model is that we know that they have certain biases. Past assessments have been done with resolutions of about 2 degrees, about 200 kilometers in horizontal resolution. This last assessment, the AR5, IPCC AR5, and also what we discussed in the National Climate Assessment, were done at a 1 degree resolution with the best models, and that's about 100 kilometers resolution. With Blue Waters, we're actually running this model now at a 25 kilometer resolution, where we can actually look at regional scale behavior in much more accuracy than before. I'll go into that in a few minutes. But one of the reasons we wanted to do that was because of known biases in the model, with the fact that you're not properly representing the orography at a resolution of 1 to 2 degrees, and that has an effect on things like precipitation. And so the models tend to have too much light rainfall and not enough heavy rainfall, typically. Another way of showing that is that the models that were used in the last IPCC assessment, this is from one of our papers, show that the models are actually in the U.S., looking at continental U.S., are actually underestimating the amount of actual increase in severe precipitation that is actually occurring. We've seen a very significant increase in precipitation coming as large precipitation events here in the Midwest and throughout most of the nation, and that is already having an effect on society. In our case, leading to more flooding in the Midwest and the Northeast, especially. Well, we want to do a better job in representing those kind of behaviors. So one of the first things that was done is to really test this new spectral element approach, which uses a cube sphere. It's a cube sphere approach to the dynamical core. And so a lot of this past year was spent in tuning and testing that approach on Blue Waters. And in the process, we learned a great deal. We're in the process now of starting the actual scientific analysis. Those were started over a month ago, where we're doing time slice runs for the 1979 to 2010 period, and at this quarter resolution I was mentioning, and then for 2070 and 2100. So basically 230-year kind of snapshots at the climate system, one looking at the past and one looking at the future for a given scenario. The RCP 8.5 scenario is basically one that assumes we continue to heavily use fossil fuels into the future. The real core to the project, though, is to run CESM at a quarter degree run with a 1 degree ocean for 150 years in the past, starting around 1850, and then to look into the future with several different realizations, different scenarios, so that we can really do very detailed analyses of both what's occurred in the past and what's could occur this century. These are likely to really be very beneficial to future climate analysis. At the same time, we're also doing uncertainty analysis to enhance the understanding of some of the key uncertainties in radiative cloud aerosol interactions, for example. You already heard about some of the difficulties in looking at the clouds in great detail. We also need to look at not only what's happening in the clouds, but how aerosols interact with the formation of clouds and also affect cloud processes. So the first goal was to replace that finite element dynamical core with the spectral element. And we've done a number of calculations with that, and found in the process as we get nearly linear scaling to processor counts up to 1 CPU per element, which is good news. But we also found some issues in that the representation of cloud forcing in the model was affected, and forcing on climate was affected, and that's believed to be connected to the parameterizations that were developed for the previous dynamical core, and so we've been adjusting those to try to, so that they're accurate for a high resolution analysis like we're doing now. That's not fully resolved, but it has come a long way to the point where we feel we can start the real scientific studies. Part of the reason this makes a difference is we look at those previous 1 to 2 degree horizontal resolution models, and those are much finer resolution models that were used in this last IPCC assessment that were available previously, just because of computational resources primarily. You can see that the resolution this cannot adequately account for all the details in orography, and that makes a huge difference in calculating precipitation, processes like precipitation. Whereas when we go to the quarter-degree resolution, which is about 25-kilometer horizontal resolution, we do get a much better representation of orography processes, orography and how that can affect various processes. With the new model, looking at some aspects of the, in detail of the, for example, the June, July, August diurnal variations in rainfall, the top is TRIM, which is a satellite observation of rainfall across region from subtropics to extratropics latitudes. And we can look at various versions of the model. This is looking at the atmospheric atmospheric component only within CESM. And looking at the 1 degree resolution versus the quarter degree resolution, there are definitely improvements in the representation of the processes and how well the model represents precipitation compared to the observations. Similarly, if we looked at the El Nino index, one of the chief El Nino indexes looks at sea surface temperatures in the Pacific. Again, the new model, which is labeled NE 120, which means a 0.25 degree resolution here, compares much better with our observations than previous versions of the model did. We also can see this in the treatment of tropical cyclones, taking again the atmospheric model running with fixed sea surface temperatures based off of full climate model studies, but now running the atmosphere at high resolution compared to the previous 1 degree resolution. We get a climatology for hurricanes and tropical cyclones that agree well with the observations, which is a good sign. And a key thing coming out of that study is that we can expect to see more higher intensity hurricanes than in the past. And that's shown by another new study coming out of NCAR that looks at, for example, Category 5, showing that the new high-resolution model is pointing to more high-intensity hurricanes. This agrees with some theoretical analysis that had been done previously, but had not really been seen in models until now. So we're in the process of setting up the model to run this period from 1850 to 2100. The background run is currently being done on Blue Waters. We think that's going to give us a great enhanced understanding of climate change, including some of these concerns about severe weather and regional effects. I want to quickly mention the analyses we're doing looking at clouds, aerosol, and radiation parameters, trying to look at all aspects of the uncertainties within that. That's being done by colleagues at the University of Maryland. And because of the timing of when Blue Waters actually occurred versus when we were supposed to start this study, rather than using CESM for these studies, we're actually using the regional model. It's called CWARF that will allow us to do these under the funding that they have. Looking at all of these uncertainties, the group at Maryland was able to get a much better representation of observations. EOP here is the optimized prediction of precipitation compared to the prior techniques. The top left was what's called the King-Frisch approach. The top right is what's called the Grell approach. Neither one could do a very accurate job in representing precipitation across the U.S., but the new optimized approach actually does this quite well. For our studies on Blue Waters, we're going to take approximately 100 of these different what's called CAR configurations of the clouds, aerosols, and radiative transfer parameters based on CWEF runs that have already been done, and then tried to look at those in more detail relative to the CESM runs, and in the process, hopefully come up with a better understanding of how the parameterizations currently used for all those processes can be better represented in a model like CESM. So I thank you. I know my time's getting short.